You might have heard of a lot of these terms: generative AI, large language models, fine-tuning, retrieval augmented generation. All of these you may have heard in sort of disparate context. Today, in this talk, we're going to set the stage, introduce what the lay of the land looks like. When do we use fine-tuning or RAG or prompt engineering? What are these, and how do they really work together with an LLM to give you the response that you need? So basically, as the title says, you'll be going from 0 to hero in 60 minutes, hopefully. Okay, so how many of you here have heard of the term generative AI, large language models? Show of hands. Okay, almost everyone. Can somebody tell me why is Gen AI and LLM both kind of intermixed and then used together? Are they the same thing? Are they different? Any thoughts? Yep.
I've always thought that LLM was back-end and then like a conversational filter with generative AI.
Almost. But that's a great answer. Now, I'll kind of do a top of the funnel to the bottom, and I'll kind of build or link the two together. So generative AI, in the term, or large language models, is a family of learning technique which belongs under artificial intelligence. Loosely put, you've heard of the term AI, but what is it? In a software definition, it is any piece of software where we can impart human intelligence into it, and is able to follow logic, either using machine learning, if-else statement, or any other transformational logic, extraction, rule definitions that we put in. But that's too broad. When people usually say AI, they're usually talking about machine learning. So machine learning is a class of AI algorithms, which you just need to feed in data sets, and the model or the algorithm is able to autonomously extract features and equations or values from that data set and is able to make predictions. So there is no really wrangling required from your side. All you have to do is create the data set. You have a bunch of inputs and some prediction output. You feed it into a machine learning algorithm, train it for a period of time, and the model learns to align the behavior of inputs and outputs. Now, there is a fundamental limitation with machine learning algorithms, which is that it only works, it works really, really well with tabular data sets and with low frequency data sets. When we talk about high fidelity or high frequency data sets or features that are large in size, like images, videos, text, machine learning really starts to fall apart a little bit. So for that, we introduce a class of learning algorithms known as deep learning. So deep learning is set to mimic how the human brain functions, which means we add more layers. You have quote-unquote neurons or weights and graphs that link two neurons together. So that's the deep learning piece of it. So deep learnings excel at sort of this classification, object detection tasks with complex input data sets. Now, this is where generative AI comes in. As you can see, with artificial intelligence, machine learning, and deep learning techniques, these are very task-oriented algorithms or learning techniques. With each of these, you had to have a data set and some outcome that you're trying to predict. Could be classification, could be regression. What I mean by that is, day to day, how many folks here have used Zillow or Redfin? So you see estimated housing price. That is more than likely a machine learning model in the back end that's trying to predict the house price based on what season it is, the location, nearby homes, all of that features go in. An example of a deep learning technique is if you've used your photo app on your phone, iPhone or Android, you may have seen the app automatically extract faces and group images of people together. That's a deep learning model working in the background. But all of those are not generative. They are task-oriented. The model in the back end is set to extract faces, and there's another model that's grouping images together. When we get to generative AI, it was introduced, or more recently, it was revolutionized by a paper which introduced a deep learning architecture called transformers. So generative AI, we feed extremely large amounts of data into a model, like internet scale data set, and we allow the model to effectively generate output, meaning generate a next token. We then use this generative capability and transform it to different types of tasks, such as classification, idea generations, etc. So when we say generative AI, it is any model that's able to generate an output based on a sequence of inputs. So if I say the capital of the United States is, the model repeats Washington, D.C. So you're not defining the task, but you're asking the model to generate the outcome. Large language models have taken over the space. You also have vision-based generative AI, known as vision transformers. They haven't revolutionized the space as much as generative large language models has, so that's why they're used kind of interchangeably today. Moving on. So what are some of the tasks that large language models excel at? So you might have heard of text generation being the most talked about task. So text generation can be write me a 2-paragraph horror story, or write me a poem about the iPhone, or something along those lines. But you also know that large language models are so generic enough that they can be used for classification tasks, such as classify this ticket into one of n categories, or classify the user's description of a product as positive or negative, and so on and so forth. You can also leverage out-of-the-box large language models to answer questions. If you have trivia questions, you can ask the model as long as it's been trained on that data set. If you go to ChatGPT or Anthropic Cloud, you may see trained until a certain date. What that means is, up until then, if that information is public, more than likely the model is aware of it. If not, it's going to answer, I don't know, it may have changed. So knowledge answering, language translation, you can ask Anthropic Cloud, Bedrock models, or even ChatGPT, hey, how do you say, let's eat omelets in a restaurant in Spanish? Translate this for me in Spanish. Or from Spanish to English. It can do all of those translations behind the scenes. I'll touch upon embeddings later, but it can also do dialogue generation. So this is where models excel at holding conversations with people. So all of these different tasks today language models have excelled at or are the state of the art. But why is it so popularized? I mean, haven't we had models before that could do this? The answer is yes. Historically, the way these tasks were accomplished is you had data set driven for a task. You would have an ML model that you would have to choose and fine-tune or train that model for several hours or days, and then get a model that's highly tuned for a given task. So for example, I have a classification model that can take in labeled input strings, such as reviews of articles on Amazon, and it's able to classify the sentiment as positive or negative. So that's one model. Maybe a text generation model can be, I input a sequence of strings or text into it, and then the model is able to summarize or generate the next sequence of embeddings from there, or next sequence of words from there. So as you can imagine, all these different tasks have different models, and maybe all of these models may be finely tuned for subtasks. Maybe one model is really great at extracting information within the software realm, another model within the financial realm, or something else. So within your organization, as it's multifaceted, you can have hundreds, if not thousands, or tens of thousands of models for a lot of these different tasks. Large language models today is now condensed, where internet scale data set is fed into an LLM. So an LLM is like, I'm forgetting the term, but LLM is like a know-it-all. It knows all of this infinite amount of information under the hood. What you could do is tune the LLM to then work to either become a text generator, or a summarizer, or an information extractor. The same LLM can be used for a lot of different tasks and use cases just with a simple API call. So how did this all come about? As I mentioned, there is a groundbreaking paper that was introduced, I think in 2017 or 2018, called Attention is All You Need. When the authors originally introduced this paper, they didn't know how famous or how groundbreaking it was going to be. But the salient points from this was they introduced a new mechanism called as self-attention. I'm just trying to find, self-attention, which allows the model to capture not only variable lengths of input, but also dependencies between the inputs in the right context. The other thing that they also kind of introduced in this paper was a model that was able to handle variable context lengths. Historically, you had large language models which had a fixed context length, and you had to kind of wrangle an input which is shorter than the context length. Let's say 1,000 words. If you only had to send 20 words into it, you had to pad the remaining and then send it in, which is just wasted computation space, or wasted computation at that point. But with transformers, you could handle variable context lengths, and you could have larger context, which started to become more usable. So you started to have C context length like 2048 or 2048, technically 2048 words, which is enough to fit sufficient information and get retrieval out of these models. So this fundamental architecture became the foundation for the very popular models that you see today, like ChatGPT-4 or Amazon Titan or Anthropic Claude. All these really powerful closed open source models are forks out of this transformer architecture. Yep.
I have the impression that LLM, the algorithm is neural network.
So neural network essentially, it is the deep neural network that we were talking about. So transformers is a branch off of the deep learning neural network architecture. So it's a way of designing encoder-decoder style networks in order to get them to generate tokens.
Okay, but it's based on neural network.
That's correct. It is based on deep learning, which is a neural network style architecture. Great question?
I have one question.
Yep.
It's a slight segue, but related. So as you're talking part like the translation for example,
Mm-hmm.
I'm just kind of curious, and this is again possibly a future question, but I know that today, for example, you native language translations, API call out, like Google or Images, et cetera. Can you elaborate? Is that something that's playing a bit more at to both support the enabling? And the concern point I have is one, there's obviously just a delay in the API calls, like you have just or Google to another 2 seconds. That's bad for real-time communication, of course. And two, third-party translation services are great, but there's Kore.ai support multiple languages natively, 100 plus. You might be able to do it more efficiently in-house. So just curious if you want to talk about your.
So that's a great question. So some of that, I think I can address that towards the end. But then let me just briefly touch on, I think you mentioned. Yeah, so one of the pieces is right now there's a lot of investment and research into multi-language, large language models like AI-21 and Jurassic models on Amazon Bedrock have multilingual large language models that can work in French, Portuguese, English, and a few other languages. They are expanding. I think the drawback right now, as far as I see within the industry, is the amount of data set that's available in other languages that are biased towards training a model. We don't have a ton of that, but there is a lot of research being invested into making the model or expanding the model's knowledge base to other languages as well. So you might see, so we can address some of those questions towards the end as well. And then I think you touched on the latency piece as well. So I'll get to that in the next set of slides. Okay, so now that you have a large language, now if any of you have thought, this sounds easy, maybe I can train my own large language model. Maybe you wanted to. What do you need to do? The first thing you're going to need is obviously data set. Now, unlike traditional learning models, like deep learning models or classification or machine learning models, you can't get away with a gig of data or a few megabytes of data. You need internet scale petabytes of data in order to train these models. So you need to first gather sources from where you can extract, Wikipedia, openly available news articles, GitHub, wherever you can find. Extract all of that data and feed it into a training pipeline. Now, a training pipeline is essentially composed of 3 things. An incoming data. You choose a language in which you want to train the model on. So Python is a very popular language, so you could stick with Python. You get a lot of support, but sometimes C++ and Java also works. You choose a machine learning library, like PyTorch, TensorFlow. And the reason why you choose that is you don't want to reinvent the wheel. There are a lot of learning algorithms, optimizers, schedulers, all of those things under the hood, which is built by researchers in the back end. You just want to be able to work off of what's already built, but nothing's stopping you from building your own machine learning libraries. Some organizations have done that, but recommended to use existing machine learning libraries. The most popular one is PyTorch. So next you start to train a model and define a metric. The metric can be, I'm going to push all of this data into a model, but how will I know it's even learning? You evaluate something known as a loss. You want the model to sequentially learn, or over time learn text sequences, grammar, and semantic relationships. And the way you would evaluate is you define some metric. Could be loss, could be accuracy, could be semantic relationship. There are a lot of metrics out there which is out of scope, but we can discuss later if you'd like to. And then keep training the model over many weeks, months, or several months in order to get the model to the state that you see in Amazon Titan or GPT-4, et cetera. Now, that's a very simplistic way of putting it out. If you actually lift under the hood, you're going to see that there are a lot of sub-steps, and every step may require some amount of specialization. You have data cleaning. You've gathered all this large amounts of data set. Most of it, you will need to sort it in a way that you can actually feed it into a training model. So there's some cleanup that's going on, some pre-processing going on. There's a process known as tokenization. Tokenization is essentially models don't understand words. They understand numbers, mathematical equations, and computations. So you need to be able to take these words, convert them into tokens, and feed them into the model. And then you actually have the model architecture. You can take what's available out on the internet. You can take Llama's architecture, or you can take Falcon's architecture, or any of the open source architecture, or you can modify it just a little bit and then tune it for your own data set. And then the most cost comes in an actual massively training the model itself. Let me give you an example of a Llama to 7 billion parametric model. It's just a 7 billion. It's called as a small version of a large language model. In full force, that's floating point 32, it requires 4 24 GB GPUs to fit the model in memory. Now, and this is with maybe a batch size of 2 at once. If you go that way, you're going to take at least a year to train the model up to some standard scale, right? Even to equal what's out there in the open source today. So what do? You increase the number of nodes that you use. You increase the number of GPUs that you use, and that's where the cost comes in. I recently read an anecdote on Twitter, or X, sorry, on X, that to fine-tune or train a Llama to 7 billion to perform decently well to open source benchmarking standards, it takes, I think, between $6 to $10 million just for the training. And this is not the research that has gone into the process of collecting data set, the process of cleaning, and all that. Lastly, when we say a model is trained and ready for inference, what do we mean? It essentially just means two things. A model graph, which is the network architecture that you define, and then weights or numbers that is part of an equation. When you send a token in, those numbers are dictating the quality of predictions that come out of the model. It's essentially numbers. So they are made in a portable format. So you can upload them into, let's say, S3, or you can upload them into Hugging Face Hub, and somebody else may be able to load them into memory and use it for inference. Now, inference also requires GPUs here. Not at the same scale that training did, but you do require maybe a fraction of those GPUs to actually run these models as inference and allow users to leverage these models on a day-to-day. Oh, that's not formatted right. The outcome, yep, go ahead. That's a great question. I'll get to that. That's a great question, and I'll address that in the next set of slides. So now a trained model, is that it? Are you done? Now that you went in, trained a model, are you good? Can you now build your own chat interface and then output the model as a service? The answer is still no. What you get out of the whole training output is what's known as a pre-trained LLM. The way I like to describe it is a pre-trained LLM is like a bachelor student. It's aware of a lot of things, but really not a master of anything. So it can follow instructions. In general, a pre-trained LLM is just great at predicting the next sequence of tokens. So let's say you've defined some parameters. You can say the capital of the USA is, and the model says Washington, D.C. If you allow it to keep continuing, it's going to say something like Washington, D.C., it's on the east coast of the United States. its population is so much because it's seen all of this in the training data set, so it's just regurgitating. Not really that useful on a day-to-day activity. So what you do is you instruct tune these models. So when we talk about ChatGPTs or Anthropic models, they're actually referring to instruct tune models. So if you, for example, use WhatsApp today, you might see Meta AI plugged in or available to chat with and ask questions. That is one example of using an instruct-tuned LLM. Or ChatGPT, if you go in and ask questions, how is it able to follow instructions? That's instruct-tuned LLMs. So the difference between instruct and chat, they're essentially instructions that you take a pre-trained LLM and you put it through a master's degree, and then out comes a more specialized model that's able to listen to you, understand instructions, and respond accordingly. So now you can ask this model, an instruct-tuned model, respond safely without using abuses or anything. And if you don't know the answer to the question, say, I don't know. So if you ask a question, it doesn't know the answer, or the guardrails haven't been met, it's going to respond back as I don't know. Whereas a pre-trained LLM will just continue to fill up the sentence. That's the difference. Why do organizations release pre-trained LLM? Is they're kind of releasing a trained bachelor student, so you can then take it and further fine-tune it on your own organization's data set. So if you've got the research funding as well as skills to do that, definitely you can take that. We've seen Bloomberg do that with Bloomberg GPT. So they have a very financially driven model. So they've taken, well, I'm speculating, they've taken some pre-trained model weights, fine-tuned them on their own corpus, and then released the model within their organization for usage for a lot of financial use cases. So an example of an instruct-tuned LLM is select all cities in the United States, in the US only, and then give it options, say New York, Chicago, Orlando, London, and Paris, and it just gives you the output for the question you have asked, nothing more. Now, with all of this said, this is what the large language model landscape looks like. But let me simplify it. Let me break it down into more simpler context. You have closed source models and open source models. Closed source model, an example is ChatGPT, Anthropic Claude. These are closed source models, which means you don't get access to the weights. You can pay to use the APIs, which means that you can send in text or you can send in data and receive responses from these models. You can also fine-tune these models, but you still don't get access to the weights, but you get access to a fine-tuned version of that model itself. On the other hand, you have open source models, meaning organizations have gone through the effort of fine-tuning and instruct-tuning these models and release these models with a license. Some have MIT 0 or CCY license, free to use within your own organization for commercial purposes. Some have a more restrictive license like Llama 2, depends on who can use it and who can't. Now, another advantage is also with open source domains, you get access to highly tuned coding models if you need to. So if there's a team of software engineers or data scientists, you can actually surface a model like StarCoder, for example, which is a pre-trained LLM fine-tuned on coding data sets. So your data scientists or your software engineers, instead of spending hours searching through Stack Overflow, they'll be able to leverage StarCoder, a model like StarCoder, or Grok, or Llama 2, or Code Llama, and just ask coding questions, and it can give you actually very accurate code samples that you can directly start to build on top of. I'll stop here and ask if there are any questions. Yep.
How much better is Llama 2 than ChatGPT in code generation? I hear it get called out, but yeah, I've been messing with ChatGPT for a long time, and it's pretty darn good.
So that's a great question, and so this is my own thought, not AWS speaking, but it's my own thought. For a lot of different use cases, ChatGPT or Anthropic Claude are just the top tier benchmarks right there. In terms of coding, personally, I have asked Anthropic Claude or ChatGPT to generate SQL code, for example. It does a fair job. It understands the context, is able to generate, but I've had to take the code and oftentimes wrangle it a little more and then execute it. On the other hand, StarCoder is one example, but there's another SQL coder model by DFog. If anybody's interested in kind of seeing how that is used, please come back to me. I have a video and a demo. But the SQL Coder model is able to generate much better SQL code from natural language. So I've given my database schema to the model and said, generate a SQL code. Actually, I just said, give me the top 10 airports in the United States, et cetera. It's able to generate based on my third normal form database that I'm able to directly execute. So there are two ways to evaluate. You can look at the pure benchmark or the coding score. They'll be pretty close to each other. Maybe these coding models will edge out the ChatGPT-like models a little more. But qualitatively, you can see that the coding models may actually be better if they're instructed properly.
This Star Coder.
Yeah, Star Coder, Code Llama, SQL Coder, there are a lot of these coding-oriented models which are open source. Yeah.
I'm fairly new, like the ECU, to the use of NoSQL Dino on AWS. What do you think is the best code-oriented model if I want to, use for the purpose of querying in Dino, for example? What would be the best most suitable?
So if you're looking at ease of use, I would say Bedrock's Claude model. If you're looking at taking more reins or more charge of what kind of model, you can even leverage, so for coding, for SQL coding, the default SQL coder, which comes in 34 billion, 7 billion parametric sizes, you can try out these. Smaller the better, but sometimes smaller models can give you false answers. The larger models are more capable and is able to give you more accurate answers. So it's a little bit of a trial and error, but you can try a 34 billion SQL coder model for something that's SQL driven. And in the instructions, you can prompt saying, I would like DynamoDB SQL queries. And so these models, if they're trained on it, which more than likely these open source models are, understand the nuances between syntaxes. Where if you're running Athena versus Dynamo, it's able to understand those nuances. And if there is, for example, I like is not a correct reserved keyword which can be used, then it wouldn't use that. So the last dimension here, yeah, go ahead.
So these star coders and these code-specific models, the way they are built is they take a general-based model like Llama 2 and fine-tune it on coding examples, or because that model has to understand the plain English and the language nuances of that. So how do they tune it?
Yeah.
How is that?
So my speculation, there are two parts. Some of this will not be available open source unless the author explicitly publishes it. Some code models are built on top of pre-trained LLMs. So you can have Code Llama, for example, which I speculate is built off of Llama 2. And then the SQL Coder model that I was just referring to is built off of Code Llama. So it's twice distilled to get you to this point. So you're right. They take a fundamental architecture because it is easier. This is the same as domain adaptation or transfer learning in models. Okay, I will move on. The last piece I wanted to talk about is all of these models comes in different sizes. It's more efficient and more cost-effective to run smaller versions of these models. So for example, Star Coder 2, I think, comes in two different flavors. So Code Llama comes in 7 billion and 34 billion. The smaller the model, the more it depends on your use case. If your use case or the scope of your use case is small, use a smaller model. It's more cost efficient. If your scope of your use case is large, maybe you're querying a massive database with a lot of relations, et cetera, then use a larger model, and you can sort of build up from there. Okay, so for those of you today that are still exploring what language models work for what use cases, or maybe just looking for ideas, there are three sort of rough pillars I like to classify use cases on. Enhancing customer experience. So things like, this is probably the lowest hanging fruit, is if today internally you have chatbots or virtual assistants surface to your employees, where they're asking questions, hey, tell me how to file for this expense report, or something like that. You can attach a large language model that with what's known as RAG, which I'll talk about in the future slide, and then surface that and make it much more easier, where the model itself is not just producing content, but also links in order for the user to take actions rather than give it generic descriptions like this is what you're supposed to do. Personalization, so you can feed in historical search results of your users internally and ask the model to suggest what could be a good recommendation. One example is if you're trying to build like an internal Netflix-like system, here's everything this user has searched. Do you want to suggest something? So the model, based on its own knowledge, is able to suggest movies that are similar in dimension. The middle part, which is boosting employee productivity, is what I'm a big advocate of. So code creation. I used to spend quite a bit of time going Stack Overflow to Stack Overflow, searching for answers and building my code. Today, I use either Bedrock's Cloud model or SQL Coder model or any of the Star Coder models in order to generate the code itself. So it has cut down the amount of time I actually spend in generating code to a couple of minutes where I can ask a question. It gives me a foundational code for me to go off of, and from there, if the code is wrong or maybe import missing, it's easier for me to fix that and then move from there.
Which one? I'm sorry, I didn't hear the name.
Anthropic Cloud, Star Coder, and Code Llama. Star Coder, Code Llama, and SQL Coder. So there are different Code Llama. Code Llama is by Meta. And the next set of slides does have that too.
Oh, great.
The last one is optimizing business processes. So document processing. Some of these large language models are capable of taking images as input. So think about a scenario where you can just post your bill, and the model is able to extract the expense, file a expense report on your behalf, and you're done. No more tedious expense report filing processes. It's also able to identify anomalies in existing cybersecurity space. So if you feed it tabular data sets or logs, it's able to identify anomalies and troubleshoot issues for you. So it's a very popular use case for cybersecurity or even log analysis, for example. Now, this is probably important, LLM adoption, right? Today, your teams may be in different stages. What works for you? Or what's the best path that works for you, right? So this is just a rough graph, but it's to generate the idea. On the left-hand side, you have accuracy. Now, accuracy here can loosely be defined as anything that's hyper-tuned to the task that you have on hand. Think about a use case where, with Amazon, if I ask Anthropic Cloud model about Amazon information, really isn't going to give me too much of info because it isn't aware of it. If that is the case, what do I need to do? I need it to be hyper-aware of Amazon information. So then I can do RAG or I can do fine-tuning. But what about a scenario where I just needed to correct my grammar or generate some code? Then probably Model API works best. So we'll just kind of do a rough exercise and dive through the journey there. So if you're looking to use models out of the box, I would suggest taking a look at Amazon Bedrock. You have a wide range of models. So you have access to AI21 Labs' Jurassic model, a very capable, I think it's a multilingual model. Amazon's Titan model. You've got Anthropic's Cloud, which is probably the premier model that a lot of our customers love to use. You've got Cohere's Command R model. More recently, they came up with a newer model which just got released. You have Meta models, Mistral models, and Stability AI's image generation model. So you can generate, if you've seen more recently the news of Sora, right? Text to video. So Stable Diffusion and Stability AI works in the same space, so I recommend giving that a try too. On the other hand, if you think that there's a model in there like Code Llama, you probably didn't see that, or Star Coder. If you think that you don't see a model in there that you'd like to leverage today, then we have the option of Amazon SageMaker, where you can easily search. I think there are 100 to 200 models available on SageMaker that are available also on Hugging Face. So we bring in the most popular Hugging Face models like Code Llama, Star Coder, etc., and make it very easy for you to click and deploy these models on SageMaker. So SageMaker is a little more, there's a little bit of management in the sense it's easy, but you can click and deploy these models and manage infrastructure. Bedrock, on the other hand, is APIs, no infrastructure management required. So that's the two differences, but you can get access to mostly all the models you need, either through Bedrock or through SageMaker. Yep.
Bedrock is like an API, but you can direct, it's an abstraction over the other models. Is that what it is?
Yes. So Bedrock is just think of it simply models hosted by Amazon under the hood. You don't have to worry about infrastructure. You don't have to worry about throughput. All of that is optimized and undifferentiated heavy lifting is done by the Amazon Bedrock team. Well, you're only concerned about generating the format and requesting the model to give you the output. Yep.
So now is the right time to ask this, but I'm a little confused about the arms race to create all these models when many of them aren't charging, right? So when you gave the cost of what it takes to either create the model or even to fine tune it, why? I mean, why are we seeing so many differences, many of which are free? What's the end game here? I mean, is it to suck you in and then charge later? Is it they think they're, I mean, I'm not understanding why there are so many of these things popping up free at such a ridiculously high cost to get them.
So I would say it's the pace of innovation, and the pace of innovation is everybody's trying to be the first or be the best. When you are the best, it opens up use cases for you. So this is me speculating.
Yeah.
With Amazon Bedrock, we realized that, there's no, well, we can kind of collate all of that together. With Bedrock, you pay as you go, which means that if you don't want to use it, you don't have to use it. You can switch over to a different API provider and run from there. So it's a pay-as-you-go model, so you're not kind of vendor locked in. But from a model perspective, I believe that it's a little bit of a philosophical question, but I believe that they're trying to get to, so large language models through this arms race of building many models, there's a lot of revolution that has happened. We've broken frontiers. Multimodality is a big thing. You're able to now process image and language together. So at some point, large language models may end up saturating. There's so much better you can go, nothing more. So now you open new frontiers with video, with audio, and then you eventually build a solution that's very generic. So you can put in whatever you want and just a prompt, and you're done.
So I have a slightly different take on it, which is that I think you're actually going to start seeing a bit of a fraction of multiple arms races. So on one hand, I think one of the first generation of arms races, who builds the biggest, largest, most comprehensive LLM out there and improve the accuracy. So everyone's kind of competing as it lands, the bar, et cetera, the GPT-3.5, Turbo 4, et cetera. And that still happens to some degree as you get aggregation of different sets of data into dimensions. Consistency, accuracy, and the way you get the associations. But I think what's starting to see the rise more, and I'm really glad that Kore talked a lot about this at the conference, because it's still not getting much of the mainstream stuff, is the rise of SLMs, and I think you're going to start seeing it's more cost effective because like GPT-4 is so short term supply. So if you can get SLMs as they can tweak to get close enough to an accuracy level that you need for the application or vertical or use case, or with a couple of points, but a significantly lower cost set and much quicker response times, I think you're going to start seeing those rise in popularity. The next point beyond that, though, is now that fraction of these monstrous aggregate LLMs are taking multiple types of utilizing text structure, text, video, et cetera, these dynamically tweaked SLMs, how do you then merge that back into an ideal state? And that's where I see kind of gold.
Yeah, that's an amazing point. Yes, I agree that like rising tide lifts all boats. So as the models get larger and larger, there's a lot of innovation put in there. So some of that innovation does distill down to smaller language models, which means that now you have models, language models, that can run on Raspberry Pis. So you've got a language model running at the edge, which is awesome. Okay, so in the interest of, I'm just going to move on. So the next step is now when you hit an API and get a model response, for most use cases, generic use cases, hey, fix this text for me, generate this code for me, it works fine. It works awesome. But sometimes, just like humans are, if I just give it a random piece of text and provide no context, the model is going to flop, right? It's going to fall flat on its face. If I give you a piece of text and say, summarize this, you don't know how many lines am I going to summarize in 3 lines, 4 lines, 5 lines? No idea. So that's where prompt engineering comes in. Prompt engineering is sort of the loose guardrails that you can put around a model. The larger the model, the more it can strictly obey the prompts that you provided. So prompt is composed of 2 things. It is composed of a certain format that the model provider has adjusted. The difference between a global instruction versus a local instruction. Global instruction can be obey the user's command, don't respond with toxic outputs, and be courteous and say I don't know. That's a global prompt. A local prompt could be classify this text for me into one of 4 categories. So that's a local prompt where you're giving local instructions. Prompt engineering is another expertise that's on the rise. You don't really need coding skills for prompt engineering. What you need here is you need to understand English and be able to frame prompts that work best. Not every prompt will work easily with the models out of the box. Sometimes you need to prompt it, get a model response, see if it works. If not, tune it a little more, and you can track these prompts along the way. At some point, the prompt really works amazingly well, and that's the prompt you take into production. There are a lot of different types of prompting techniques. The ones which I would point you towards is basic prompting, which is just fix this code for me, find this bug for me, etc. Question and answers and text summarization, as the name suggests, very straightforward. The ones that are really important is chain of thought prompting, where you ask a model maybe a math question, and it's able to respond back. If Susie had 6 apples, took away 2, how many does Susie have? So it responds back with an answer. But now you ask it to reason. Tell me why you think that is, and it's able to provide that response. One use case for that could be, I asked a model, so we were doing a ticket classification system. The model started to classify the tickets into categories. Now I want to know why it classified that. What did you see in the vast amount of data set that made you think that? So we added a chain of thought. So then it gave me the classification, and it gave me the reason for that classification. So now my customers are able to look at the classification, look if the model is right, go back and do a postmortem to see if that is correct, and then approve or disapprove. Then you have few shot prompting. So if there is a task, a little bit of a complex task that you want the model to perform, just like humans, you got to instruct it, provide a few examples, and then allow the model to take it from there. So that's few shot prompting. Zero shot is right out of the box. The instruction is clear enough. It knows how to prompt. Here's an example of what a prompt would look like. On the left-hand side, you have a classifier prompt, right? The sys, I don't know if you can see this, but the sys right there is the global instruction. An assistant is an expert reviewer, responds back with 1s and 0s. Here are some examples. This is what I need from you. And now I provided newer input, and the model is going to respond back with 1 or 0. That's it. On the right-hand side, you have a Q&A prompt, very similar in structure, global and local prompts that can respond back. The third piece of this is retrieval augmented generation. Now, once you've done prompt engineering, the model is able to respond back with answers the way you expect it to. But if I ask a Llama 2 model trained back in 2022, a year from now, who's going to be the president of the United States, it wouldn't know what to answer. It's out of date. Maybe it would answer Joe Biden, but maybe not. I don't know. So for that, how do you make it more current? You add what's known as retrieval augmented generation, which is essentially a high-level task, provided some additional context, where the model can search for the answers within that and provide a response back. So the retrieval part is retrieving context that's relevant to the question. Augmentation is adding the context into the overall prompt so the model can search. And generation is the answer that it's giving out. So why is it useful? You can adapt it to the domain or task at hand. That's why it's important. So if you have a Llama 2 model, do you need to fine-tune it to make it work for healthcare or finance? The answer is probably not. You can improve the context of the model and ask it to only respond based on the context it has got. You can ask it to enhance the performance on certain tasks. You can even ask it to provide coding solutions based on some reference code you provided. Lastly, improve context awareness. Like I said, more up-to-date information. You don't have to keep fine-tuning the model. It's an ever-changing goalpost. So you can improve the model's response based on RAG context. So the information extraction. This is critical. When we say who's the president of these United States, 2 years from now, there are a couple of different ways where you can extract relevant information. You do rule-based, which you might have seen with knowledge-based article search systems that you have today. Search for a word, it'll highlight every context of that word. Or structured data, which is SQL. You can ask a model to generate SQL, extract tables, and feed that into the model. The last one, which is what's really popular, which is semantic search, where you take a bunch of documents, feed it into a model, generate some latent embeddings. What is that latent embedding? It's capturing a sequence of numbers that's capturing the information that it's provided with. So it could be like New York, Subway or Statue of Liberty. These are all semantic relationships between, because it's in New York with those components. So the next time you search New York, all these information may be extracted out. So high level, this is what it looks like. You feed the information, you get a defined sequence of numbers as outputs. So those are known as vector embeddings. And those vector embeddings is what we store in a vector database for retrieval. So this is the full action of what a RAG is. You have your existing data sources, can be PDFs, can be SQL tables, can be files, whatever has text in it qualifies as a data source. You chunk the document. With models with larger context sizes, you don't need to really chunk them, but it is always recommended to chunk. Otherwise, you might have, if you're looking for Subway, it might be maybe one paragraph in a massive document. You don't need the whole document to answer that context, which is right there in the second paragraph. So you chunk it, so you retrieve relevant pieces of information. You pass it through an embedding model, so you create an embedding, so you're not just searching for raw text, and you put it in a vector store. Why vector store? Because it's hyper-optimized for storing and running calculation using high-dimension data sets, just like this. Yep. Yes, there is. If you're interested, there's a Hugging Face embedding leaderboard, embedding model leaderboard. Just like you have a text generation leaderboard, there's an embedding model leaderboard. I think there's a BGE model, the last I saw was the top model there, which means that it was really accurate at extracting.
So one thing I was wondering, so if you have, let's say, pediatrics information there, okay, and a small piece of information is changing, like Mary has 9 apples, but now it's let's say where it is, okay? So obviously, if that information is chunked, it said, okay, I know where that information is, and it's stored in the vector store, okay? Next time it goes to retrieve it, though, so we ask the question, how many apples it's already had, and also the variable change to 10. Because it's just a variable change is not significant, is it still an existing data vector store pieces, or does it actually have to retrain that information?
No, so there are a couple of schools of thought for this. One is if the model is smart enough or more mature enough, you can put both. You can put the older context where Mary has 9 apples or Mary has 10 apples, and the model is able to see that, hey, there are identical phrases. So right now, Mary has 10 apples, so that's what I'm going to answer. And you can add the chain of thought into it and then validate whether that's correct. Okay, so you've got, yeah. You can append or re-index. You can append or re-index. So when we feed it into the context, both, that's an append, where you can add an existing piece of information and just call it a day. Or you have to search that blob, and you have to keep all those different pieces intact, where you've got to search that exact piece of blob and update it. Exactly, so that's the key piece. So you've got 1 more minute. Is everybody okay taking another few minutes, or? Okay, are we good? Okay, all right. So what next, right? When we ask a question, when a user asks a question, the question itself is converted into an embedding under the hood, right? So who's the president of the United States? So president, United States, semantic relation. It goes out into the vector store, retrieves all pieces of information that's relevant to that, builds a context, feeds it back into the model, builds it with the prompt where it says, here's the task. Answer only based on the context. Here's the context. Now generate an answer. And that's what the model will respond back. Any questions around this? Okay. Now, this is RAG, right? Now you feed the model is aware, it's able to answer questions back. The last step is fine-tuning. When do you fine-tune a model? To me, fine-tuning comes in when the RAG framework that you've currently developed is not sufficient enough, or the model is not aware enough. Let's say a scenario where you have your document corpus has a bunch of jargons, like your organizational jargons, and no definitions available. Like if I say, oh, hey, can you give me all customers that are tagged as GFI? The model says, I don't know what GFI is. So you got to keep defining these jargons one after the other, or build this complex relationship where it's able to reference what the acronyms are or jargons are, get that information, go back to the vector store. It's messy. What would be easier is if you can take a model, fine-tune it, where you have all this data set built in that you can prepare as a fine-tunable data, and change the weights. So fine-tuning is essentially changing the weights. If a model vendor pushed weights out as 1, 2, 3, 5. You just optimized it and made it 1, 2, 3, 6. Right? You changed it a little bit. If you fine-tune it well enough, and there are a lot of best practices and state-of-the-art, you don't really change the core foundation of the model. You keep it intact. You only change the auxiliary regions of the model, which means that the core information is still kept intact, but your model is only responding differently either to prompts or formats, etc. Fine-tuning is also the mechanism that's used to take a model from pre-training to instruct tuning. So you take your instruct-tune data set, format it, and send a pre-trained model through the fine-tuning cycle. So if a vendor releases a fine-tuned, instruct-tuned model, they just perform some fine-tuning on that data. Yeah.
More than just changing the weights, because in the jargon example you gave, how does the jargon get in? Are you augmenting the model with your jargon and then adjusting the weights?
Yeah, so those jargons that you just introduced within your data set, the model will learn to understand what those jargons are. Exactly. So the weight change is just that. It's these texts that are transforming into weight changes.
And this process is not very expensive, I guess.
Depends. If you're doing LoRa-based fine-tuning, which I'll just get to in a second, it's not that expensive. Maybe $200 to fully adapt it to your organization. If you're pre-training or changing the weights of the entire model, that may be more expensive. So basically what you're doing is sending a master's degree holder to postdoc. Maybe, yeah, you could change them a little bit. It's not that expensive to do it. And maybe you might get a much better model. Here's a great example. What drives sales growth at Amazon, right? On the left-hand side, you see a generic answer from GPT-6J. GPT-J 6 billion. Like out of the box, not fine-tuned. Very generic answer, but when you fine-tune it, you get a little more context, a little more response, a lot more clarity. So that makes the difference. Is this enough? Is the left hand enough for your organization? Great, you can use it out of the box. No fine-tuning required. But if you need answers like that, then you have to push it through fine-tuning, evaluate the model, and then send it. So just to be safe and not change the weights that a vendor just spent millions of dollars optimizing, there's something known as performance-efficient fine-tuning. So like I said, a 7 billion model fit into memory is not cost-effective. It takes you 4 GPUs just to fit a 7 billion model. Think about 180 billion, 350 billion. What do we do there? It's completely out of reach? Probably not. The way you can fine-tune is known as performance and efficient fine-tuning, and there are two distinct methods known as LoRa and QLoRa. What is LoRa? Here you have your pre-trained weights. You don't touch it. I'm simplifying. You don't touch the pre-trained weights. You add auxiliary layers or linear layers on top, which is called weight update. So when you fine-tune it, you only change the auxiliary weights and not the base weights. An analogy I'd like to put is I've got a $10,000 motorbike with only one seat, and my friend says, I want to ride with you. You're not going to take apart the bike and put a new seat in. You put a sidecar. That's exactly what this is. It's a sidecar to your bike. So the sidecar is such that you keep them separate. You have your base weights and you have what's known as LoRa adapters. And then when you need it for a particular task, you just load the adapters, and the adapters are a fraction of the large model size. So if the large model is 70 gigs, the adapter is about a gig. So this is how you have a mini sidecar weights that are going in. So one thing to note is you're only fine-tuning about 1% of the parameters, less than 1% of the parameters. Now, even that can get very expensive in floating point 32, meaning full-blown all weights, all floating point 32-bit accuracy. Sometimes that's not going to work too, because you don't want to invest so much to just fine-tune. So there's a method called quantization. All that is doing is approximating your numbers. So on the left-hand side is maybe FP32 weights. On the right-hand side is when you approximate, it converts it into 4-bit, 8-bit numbers. So you're making a little bit of approximation, but these models are accurate enough that these approximations don't really take away from the quality of output it produces. If you get bad outputs, more than likely it's coming from the quantization. Then you do the same thing with quantized low-ranking adaptation, or QLoRa. So this allows you to quantize and build that sidecar for your given model. What that results in is a 65 billion llama model can fit in one 48 GB GPU. which is crazy. It was 7 billion on 4 GPUs. Now you have a 65 billion, and you can fit them, now you have 24 GB per GPU. You can fit 2 of those in a single machine. Okay, last piece, and I'll kind of burn through this, is responsible AI. So I like to say with great power comes great responsibility, is if you've got a really powerful model, you need to ensure that the model isn't hallucinating, it's not producing output and generating output from its own headspace, and it's grounded in reality, and that's where RAG really helps, where you can provide the document references where it's generating that from. You want to ensure that open source models especially, you want to ensure that these models are not toxic and provide safe outputs, that they're not racially biased, they're not racially charged, they're not producing answers that can be hurtful, especially if you surface this internally or externally to public. Making sure that the data, if you train your model on, is not surfacing the intellectual property itself. So you can provide prompt guardrails, fine-tuning to not allow it to surface important info. Finally, data privacy. You want to ensure that your model and your weights, if it's proprietary, are not leaked. So there are about 6 pillars for this. Fairness, either through prompt or through your training data set, ensure that your model is responding fairly to all requests, meaning it's again, not racially biased in any way. Explainability is a very important piece, so adding things like chain of thought so it explains its answers. So sometimes models' output can be perceived as harmful, but sometimes it's grounded in data. How do we differentiate? You want to be able to provide that explainability as an output in the model, as an output from the model. Now, robustness is sort of loose. Robustness is how good your model is able to respond to input queries based on different contexts, etc. Privacy, governance, and transparency, as the name indicates. Very straightforward. Now, just last piece of kind of suggestion, if you're building models, how do you build them safely and responsibly? The first thing I would do is define a use case and put the guardrails. Like this LLM chatbot that I have is only going to work within the scope. Like for example, there's an LLM chatbot that was surfaced by one of the companies, one of the vendors as an assistant to selling cars, right? So you want to know what is the scope. Can it really sell cars? Can it only produce information to help the customer? So you want to define the guardrails very, very strictly. Prioritize and educate. You want to tell your internal as well as external users that this is a chatbot. It is not a human responding. Sometimes it may be wrong. Please cross-check the answers. And you need to train internally that sometimes the models may hallucinate, or you might want to prevent or build in guardrails against prompt injection and prompt hacking.
Such as Salmi power dollars and
Yeah. Test, very important piece. You got to test a wide variety of prompt, ensure that there's no jailbreaking happening. Continue to iterate, so you got to keep improving the model, keep evaluating it. So FMOps is a very crucial piece. And lastly, governance policies and accountability measures as a part of your system. There are 2 policies. There's risk management, NIST RMF management framework that provides some amount of references around responsible AI. And there's a forthcoming ISO 42001 standard. It may be out, so I would check that. But there are 2 kind of high-level documentation to allow you to develop responsible AI. But that's it. Thank you so much, folks.